Okay, so welcome back to this next video in which we are discussing the finite cyclic groups. Okay, right, so we've discussed that the finite cyclic groups are an entire class of groups, okay, and they're denoted C little n, where little n can range of the natural numbers, so it can be 1, 2, 3, 4, 5, etc. Okay, and the way that you construct C little n is what you do is you create the set containing 1, 2, 3, all the way up to little n. Okay, so all the natural numbers up to little n. And then basically what you do is you look at all the cyclic permutations of this set of little n elements. You give those cyclic permutation symbols, you put those symbols into a set, and that's going to be the set that will form your group C little n, basically. Okay, the composition law that you are going to define on this set of symbols is just compose the two cyclic permutations that they represent together, okay, get the answer, and then that answer will be another cyclic permutation, and then just put in the symbol that represents that new cyclic permutation in the composition table. Okay, we've then discussed what a cyclic permutation actually is. What you can think about doing is just putting the n little elements of this set around the edge of a disk, and then the cyclic permutations of the elements of this set are the permutations that you can create just by rotating the disk around by a certain multiple of the angle 360 divided by n, basically. Okay, and that means that in total there are n different cyclic permutations, including the identity permutation here. Okay, and those are all going to be represented by separate symbols in our group Cn. Okay, and when you compose any two of those together, it will give you another cyclic permutation, so it will give you another symbol from this set, basically. Okay, and we've discussed how these general C little n groups obey the axioms of group theory, and in fact they obey an additional axiom, they obey commutativity, so they are in fact abelian groups. Okay, so to illustrate all of these points that we've been discussing in general now, what I want to do is go over some examples. So we'll just start from the bottom basically and work up. So we'll start with C1, okay? So here we're going to start off with a very simple set. We can start off with a set containing one element, which is just the symbol 1. Okay, what we'll do is create our little disk here, and the only symbol we're going to be putting on our disk is 1 itself. Okay, so what permutations can you create now? Well, all you can do is rotate by 360 degrees, but of course rotating by 360 degrees you might as well not rotate at all. Okay, so the only, and I'm sorry about that, the only permutation that you can actually create is where you map 1 onto 1. Okay, we can give this permutation a name, we'll give it the name I for identity permutation. We put this symbol into a set here by itself. Here is the identity in this symbol. This is going to be our set called C1, okay, and then we'll have a composition law defined on this, okay, which I'll give the symbol abstract composition. We'll put all the elements of the set here along like so, okay, and there's only one element, so there's only one possible composition, and that's the identity composed with the identity, meaning do the identity and then do the identity again, which overall just gives you the identity basically. When you send 1 to 1 and then 1 to 1 again, overall the effect is that you've sent 1 to 1. Okay, so there is our C1 group, and you will see that C1 is exactly the same as S1 basically, so there's no difference between them. Okay, so in the case of S1 there is only one permutation of this set containing one element, and that is a cyclic permutation, so C1 and S1 are exactly the same. Okay, it's the same story for C2, but slightly more interesting C2. So what we'll do is create a set now containing two elements. Okay, so we'll have 1 and 2 in a set together. Okay, and again what we'll do is we'll draw out our little disk here, and now we'll put the two symbols at the opposite side of the disk. So we'll have 1 up here and 2 down here. Okay, now we can create some more interesting permutations. So firstly, we can rotate by 0 degrees or 360 degrees, whichever one you want to view it as, and that will just send 1 to 1 and 2 to 2. Okay, so that's one cyclic permutation that we can achieve here. Again, we'll call that the identity permutation. So here is our identity permutation. But the more interesting cyclic permutation that we can now create when we've got two elements like so is that we can rotate around by 180 degrees, and that will map 1 onto 2 and 2 onto 1. Okay, so let's write that out. So 1 will go onto 2 and 2 will go onto 1. Okay, and we usually call that the transposition permutation, tau. Okay, but we could think of it as the rotation by 180 degrees. Okay, so to create then the group C2, what we'll do is we'll stick into a set these two symbols, the identity and tau, which are representing these cyclic set permutations. Okay, and then we just need to define our composition law here. So here's our composition table for C2. So we'll have the two elements up here and down here also. And then let's go through all of the compositions. We know that the identity elements will compose on either side with any other element just to give that other element back again, because whenever you compose the identity permutation with any other permutation, the net result is just giving that other permutation back again. So the identity composed with identity, of course, will equal the identity. The identity composed with tau means do tau first, then do the identity. Okay, that, of course, overall gives us tau, and tau composed with the identity just means do the identity first and then do tau. Okay, and that again just gives us tau. The only interesting one then is tau composed with tau, which means rotate by 180 degrees and then rotate by 180 degrees again. Of course, that means rotate by 360 degrees, so that overall returns us back to the identity. Okay, so it is helpful to think of things in terms of rotations. It makes this composition table very intuitive. Okay, so here is our group C2, and again, those of you who have watched my video on S2, or if you're just familiar with the symmetric groups, you will realise that this is exactly the same as S2. Okay, right, now we get more interesting, okay, because C3 is actually going to be different from S3. Okay, so C3, what we're going to do is create the set containing three things, 1, 2, and 3, and now we're going to put these three things around the edge of our disk here. So here's our disk. We'll put 1 up here, we'll put 2 here, so the angle will be 120 degrees here, 360 divided by 3, and then we'll put 3 over here. Okay, so they're all spaced, or they're meant to be spaced 120 degrees apart. Obviously I've just done this by eye, but in principle they should be spaced 120 degrees apart. Okay, right, so what permutations can we create? Well, of course, instantly we know that we'll get the identity permutation here by rotating by either 0 degrees or 360 degrees or any multiple of 360 degrees. Okay, so there's our identity permutation. Once again, we'll just call that the identity here, I. Okay, now, what other permutations can we get? Well, we can get the rotation by 120 degrees. Now, what do you get if you rotate by 120 degrees? Well, let's think about this. So if I just draw the numbers out ready, where does 1 go when we rotate by 120 degrees? It will go to where 2 is. Okay, where does 2 go? Well, it will go to where 3 is. And where does 3 go? Well, it will go to where 1 is. Okay, and we will call that rotation by 120 degrees sigma. That's the common way that you denote rotation, basically. Okay, so we'll call this sigma. Okay, then there is the other cyclic permutation that's left, and we know that C3 will be size 3. There's going to be 3 cyclic permutations. We've already discussed that for the general C little m. Okay, now there is the other one, which is rotate by 240 degrees, okay, which is sigma squared, basically, rotate by 120 degrees twice. Okay, where will this map everything onto? Okay, well, it will map 1, of course, onto 3. Okay, where will 2 go? It will go onto 1. And where will 3 go? Well, when we rotate it by 240 degrees, it will go to 2. Okay, so this is sigma squared here. Okay, and those are the 3 cyclic permutations of this set of 3 things, basically. Okay, so what we'll now do to create C3 is we'll stick all of these into a set. So we'll have the identity, sigma, and sigma squared, and we'll need to create the composition table. So let's just do that now. So the composition table is gradually getting larger. So we'll have all the elements up here, I, sigma, sigma squared, I sigma squared, and there's loads of easy answers that we can fill in straight away. So when we compose the identity with any of these elements, of course, we'll just get them back again. So the identity composed with the identity means do the identity twice. That, of course, is the identity. The identity composed with sigma means do sigma and then do the identity. Rotate by 120 degrees and then rotate by nothing. That's overall still rotating by 120 degrees, and so on. Rotate by 240 degrees and then rotate by nothing, that's still rotate by 240 degrees, and the same is true down here. This time sigma composed with the identity means do the identity first, rotate by nothing, then rotate by 90 degrees. The net result is that we rotate by 90 degrees. Sigma squared composed with identity again means do nothing, rotate by nothing, and then rotate by 240 degrees. The net result is that we rotate by 240 degrees. Okay, now let's fill in the other four entries. Sigma composed with sigma, well, we know, of course, what that is. That's just sigma squared, so rotate by 120 degrees and then rotate by 120 degrees again, and you'll get rotate by 240 degrees. These are more interesting. Sigma composed with sigma squared, this means rotate by 240 degrees and then rotate by 120 degrees. Well, that's now rotating by 360 degrees, so that returns us back to the identity. The same is true for sigma squared composed with sigma. We know, of course, that the group is abelian. Okay, so we know that the entry here has to be the same, but of course this just means rotate by 90, sorry, not rotate by 90, rotate by 120 degrees and then rotate by 240 degrees, and that will mean, again, rotating by 360 degrees. Then finally, sigma squared composed with sigma squared means rotate by 240 degrees and then rotate by 240 degrees again. That means that we're overall going to rotate by 480 degrees, which is the equivalent to rotating by 120 degrees. So that's sigma there. Okay, right, so this is the group C3, and this is not the same as S3. Okay, S3 is bigger than that. S3 contains all the transpositions as well. So S3 contains the permutations where you just swap two of the elements and hold one the same. So for instance, it will contain the element like so. Okay, so I draw one of the elements that is in S3 but not in C3. Okay, so it will contain the transposition of 1 and 2, but then you hold 3 constant. Basically, that's not in C3. Okay, you cannot swap 1 and 2 and hold 3 constants by rotating this disk. There's no way of doing that, not without breaking the nail and flipping the disk over, and you're not allowed to do that. You're only allowed to rotate the disk. So you simply cannot get this permutation in this way. Okay, so that is not within C3 basically, but it is in S3. And there are other transpositions as well, so for instance the transposition of 1 and 3 and the transposition of 2 and 3, which are also in S3 but not in C3. Okay, so this is a smaller group of symbols representing permutations of the set of 3 things than the S3 group basically. Okay, right. We'll do one more, I think. We'll go on to C4, and then hopefully you'll get the idea from there. Okay, right. So we never went into S4 when we did the symmetric group of 4 elements, mainly because it was just too enormous, basically, to go through. Okay, but C4 is handleable, basically. It's only got 4 elements, so it's manageable. Okay, right, so once again what we'll do is create the set now of 4 elements, so 1, 2, 3 and 4, okay. Then what we'll do is we'll put these around the edge of a disk. Now what's our angle going to be this time? Well, there'll be 360 divided by 4 this time, so there'll be 90 degrees. So we'll have 1 up here, we'll have 2 here, we'll have 3 here, and we'll have 4 here. Okay, they're spaced at right angles apart from one another. Okay, right. So now let's think about the cyclic permutations that we have. Well, of course, once again, we'll have the identity permutation where we just rotate by nothing. So 1 goes to 1, 2 goes to 2, 3 goes to 3, and 4 goes to 4. And I think I'll just draw these out again, okay, for the sake of making it very concrete. Okay, so 1 will go to 1, 2 will go to 2, 3 will go to 3, and 4 will go to 4, so we'll have the identity there. Okay, so we'll call that set permutation I as usual. Okay, next we'll have the rotation by 90 degrees, and again we'll use the same notation for this. We'll let sigma represent the rotation by the smallest angle, basically, and then we can express all the other rotations as powers of sigma, basically. And that's standard notation for the elements of cyclic groups. Okay, right, what will we do when we rotate by 90? Well, of course, 1 will go to 2, 2 will go to 3, 3 will go to 4, and then 4, of course, will go back to 1. Okay, so we'll call this element now sigma. Okay, rotation by the smallest angle that you can here. Okay, then the next one will be rotation by 180 degrees, which is just do sigma twice, basically. Okay, so let's show this. So 1, 2, 3, 4, and 1, 2, 3, 4. So 1 this time will go to where 3 is when we rotate round by 180 degrees. 2 will go to where 4 is. Okay, 3 will go to where 1 is. And 4 will go to where 2 is. Okay, like so. And that now is the element sigma squared, because it is just sigma composed with sigma, basically. Okay, and then finally we'll have rotation by 270 degrees, okay, which is sigma to the power of 3 this time, sigma composed with sigma composed with sigma, okay, and basically where will everything go this time? Well, 1 will go to where 4 is, all the way around by 270 degrees, 2 will go to where 1 is, okay, all the way around by 270 degrees, 3 will go to where 2 is, and 4 will go to where 3 is. And I should just stress that you'll notice that this rotation clockwise by 270 degrees is the same as rotation anti-clockwise by 90 degrees, and that's why we haven't ever had to think about anti-clockwise rotations when we've been doing these cyclic groups. You might have been wondering, why are you not thinking about anti-clockwise rotations? Okay, well, it's because you can achieve anti-clockwise rotations by the clockwise rotations, so we'd have just been considering degenerate cases if we'd have considered the anti-clockwise rotations, which is why I've always been thinking in terms of clockwise rotations. Okay, but that's why we don't need to worry about them, because we've got them covered basically in a way. Okay, right, so this we'll call now sigma cube here. So these now are going to be the 4 symbols that we are now going to put into our group C4. So C4 is now going to be the set consisting of these symbols I, sigma, sigma squared, and sigma cubed. Okay, and we'll have a composition law defined on this, which again we'll just denote as abstract composition, and we will want to define what all of these composed with one another is, and we will of course work this out from the set permutations which they are representing. Okay, right, so again we can easily fill in what the identity element composed with any of these elements are, so I'll just do that. So it takes them all to themselves, and again this column here, any element composed with the identity will just give that any element back again, so we're familiar hopefully with that by now. Okay, right, now let's fill in the other ones. So sigma composed with sigma means rotate by 90 and then rotate by 90 again, so that's overall rotate by 180, that's sigma squared. Sigma composed with sigma squared means rotate by 180 degrees and then rotate by 90, of course that's the same as rotating by 270. Sigma composed with sigma cubed means rotate by 270 and then rotate by 90, which of course is rotating by 360, or rotating by nothing, the identity element. Okay, next up down here, we'll have sigma squared composed with sigma. That means rotate by 90 and then rotate by 180. That's the same as rotating by 270. Then we've got sigma squared composed with sigma squared, rotate by 180 degrees and then rotate by 180 degrees again. That's rotating by 360 degrees or nothing, effectively. Okay, then we'll have sigma squared composed with sigma to the power of 3. That means rotate by 270 degrees and then rotate by 180 degrees. That now is equivalent just to rotating by 90 degrees, because the rotation by 360 degrees doesn't do anything, and then you'll rotate on top of that by another 90 degrees, and that's now reducing you back to just being overall rotating by 90 degrees. Sigma cubed composed with sigma, that's rotate by 90 and then rotate by 270, that's the identity. sigma cubed composed with sigma squared, that's rotate by 180, then rotate by 270, again that's overall net rotating by 90, and then sigma cubed composed with sigma cubed, rotate by 270, then rotate by 270 again, overall what does that do? We rotate by 270, then we rotate by 270 again, that's taking us to rotating by 180. Sigma squared, basically. Okay, so here is our composition table on this group C4, basically. Okay, right, and that's certainly not equal to S4. S4 is massive, it's got 24 elements. C4's only got 4 elements. Okay, and again, you can easily come up with examples of permutations that would have to be represented in S4, which are not represented here. For instance, you could just have the permutation where you swap 1 and 2 around, but hold 3 and 4 constant. That's not represented at any point in here, so you can easily dream up other permutations of this set of 4 elements which are not represented in this set of 4 permutations here. Okay, but as you can see from the composition table, this is closed. Whenever you compose any of these together, you get another one back again. Okay, so it does form a beautiful group, and indeed, you can continue this on. You can go into C5, C6, C7, C8. The key thing to understand is that the reason it is closed is because whenever you compose one of these cyclic permutations, which you can think of as a rotation, with another cyclic permutation, which you can think of as another rotation, you end up with a rotation. Okay, so you end up with another cyclic permutation. Okay, right, so that now concludes our discussion of finite cyclic groups.